This is booting up. Let me welcome everybody to the fifth Emerging Research Showcase. Excited to be a part of this fifth one. The Plant Sciences Initiative kind of kickstarted this with the first ERS, and we've progressed now to another rotation. So excited to kind of be a part of this one. The next Emerging Research Showcase, if you'd like to put it on your calendar, is on February 4th, 2021. And hopefully 21 will bring us better luck than 2020. We'll plan for a virtual ERS on February 4th, and maybe with our fingers crossed and all the ducks aligned, maybe it won't be virtual, but I bet it will be. So nevertheless, mark that on your calendar. You'll get more details as we get moving. And secondly, and Deborah will also hit on this, after this Emerging Research Showcase, we have an opportunity to have a networking platform that Deborah will describe, and hopefully you all can stay engaged for at least part of that, if not all of that, at the end of this Emerging Research Showcase. So thank you very much again. Let me start off with a Plant Science Initiative update. Several of you are engaged with the Plant Science Initiative heavily, and what I'm telling you or will tell you is not news to you. But I also know that several of you are not day to day on the PSI or month to month, and so let me kind of give you some opportunity here to get you caught up to kind of where we are. I think all of you have seen this, our vision, mission, guiding principle statement. The bottom line here is we are going to be the best plant science research facility and staff and coming up with results in the world. And we're going to do that as we strive for excellence, both in our academic, our outreach, and our research mission here at NC State. So excited to be a part of this. Let me give you just some touch point updates. Several of you again know these, but as most of you are aware, we were in the search for a executive director for the North Carolina Plant Science Initiative. This is to be the person that comes in and replaces me. We were well on the way to identifying that person to come in and interview. And lo and behold, when COVID hit, we were down to our final three candidates. And because of the travel restrictions, the university restrictions on meetings, we kind of had to put that search on hold. But I'm excited to tell you that we have three well-renowned plant scientists ready to take the next step and come in to do a live interview at NC State. Once that happens, obviously their names will become public, and all of you will understand who those are. But in the meantime, before we made their names public, we wanted to kind of put this on pause until we know we can get them in for the final interview. Now, uncertainty is still kind of playing into our cards here, as we really don't know when we'll be able to live interview these. So we're taking a look at several options of maybe getting these three finalists pushed to at least a final stage that we could make an offer to one of these people. So stay tuned. I am surely hoping we can get this person on board in the first quarter, or at least the first half of 2021, if we keep our fingers crossed and all things align. But I'm excited. Each of these candidates brings a unique skill set, but I think all of them bring the leadership skills that we are looking for the North Carolina Plant Science Initiative Executive Director. I'm also excited to announce we have appointed Jeff Bach. All of you know Jeff, or will know Jeff, as the Interim Director of Operations for the initiative, specifically for the Plant Science Building. As you imagine, when you construct a $160 million building, you have a lot of moving parts going on in the building, from people movement, equipment movement, room assignments, equipment maintenance, you name it. And so Jeff, the master of keeping a lot of balls in the air and does a really good job on just day-to-day stuff, will assume that operational director when currently, but specifically when the building gets ready to open and after it opens. You'll get to hear from our four platform directors. We have four scientists appointed to this, and you'll get to hear live from each of them. And so I won't steal their thunder, but this was a big move forward as well for the initiative. Because we were on hold for the executive director search, we needed to pull the trigger fairly quickly to get some science leadership into the initiative. And I'm excited that we have these 4 individuals providing that science leadership. They were appointed mid to late summer and have fully engaged and have gotten grasp of the initiative and in their unique areas and providing some great guidance and great input thus far. So you'll get to hear from each of them. And then last but not least, some of you are involved with our CIRSA efforts. This is the proposed Center of Excellence for Regulatory Science and Agriculture. This sits under the Plant Sciences Initiative, and I'm happy to say that Dr. Dinah Seth Carley, along with some assistance from Jeff Bach, have really got the balls rolling on this CIRSA program. They are in the midst and final midst of putting a board of directors together, an executive council together. They're continuing to run seminars and symposium. And I know Denisha had some big plans for possible internships in 2020 that we've had to postpone. But this has really gained a lot of steam and speed and excitement around the ag community, not only here locally, but also nationally. And I'm pretty excited about that. Again, I won't spend much time on this because I'm going to have each of the platform directors kind of introduce themselves. But basically, we had always planned on having 3 platform directors, one that would be looking after plant improvement, one after the data-driven plant science, and then one after resilient ag systems. After consulting constituents, growers, consumers, administration, and also relying on Dr. Al Rebar, who retired here as the Vice Chancellor of Research, we decided a critical missing component here was the academic and outreach platform. And so we've added that 4th platform, and Dr. Hannah Burrack is heading that platform up. So I won't spend much time on this, but excited. This is a huge step forward for the initiative to get some science leadership involved with the Plant Science Initiative. All of you were aware in 2019, the university gathered some money under the Office of Research and Commercialization, innovation, and we collected about $2.4 million from several deans around the campus, from the Office of Research and Innovation, from the Keenan Institute, and the goal in the provost, and the goal here was to have some startup money for possible projects that faculty, interdisciplinary projects that faculty would put together and pitch for this pot of money. We initially set out to maybe fund 3 of these. We ended up, we couldn't get 3, but we had 4 solid teams that were chosen. We had about 200 distinct faculty in 17 different original applications apply for this money. So right away, it should tell you, it told me that we had a true interdisciplinary effort across this university with multiple colleges, multiple departments, and again, about 200 different individuals vying for this money. You can see here the 4 winning GRIP teams that were notified of this in early 2020. And I will tell you that they're well on their way of getting staff, whether it's doctorate students or postdocs. They're well on their way to getting their teams organized, and some of them have already gotten some early results on some of their projects here. But we're excited here about the diversity of these projects. I'm excited about some of these really taking hold and changing the face of agriculture on specific things. So excited about that. The carrot, if you will, at the end of the stick was these teams have the opportunity to really be the inaugural occupants of the plant science building if they wish. The building will be open in early 22, and these projects will be probably about half to 2/3 the way done. So they may elect not to go in the building, but they do have the opportunity to go in there if they wish. Some other exciting news that I want to announce. We signed a formal agreement with SAS. That's our next door neighbor here in the Raleigh-Cary area in November of 19. And then soon after that, engaged kind of a summit between SAS, Microsoft, and NC State. And this 3-way partnership here concluded here with a signed MOU in August of 2020. And so I'm excited to say from an NC State perspective, we have 2 fantastic global partners that are going to assist and help us along the way as we engage deeper and deeper in this whole data analytics piece of agriculture. So to have SAS and Microsoft on board working with us side by side with some of our faculty and our science researchers is just a tremendous effort. To get us going, you had to start somewhere. The SAS and Microsoft science teams, individually as companies, I gave them a list of 8 to 10 projects that maybe we could get our teeth cut on, and they both individually selected the work by the team led by Ralph Dean. And the title of that project is the Development and Integration of Sensor Technology for the Early Detection of Plant Disease and Foodborne Contaminants. So these teams, this team made up of NC State, SAS, and Microsoft meet periodically. They're working through some of the issues. And bottom line here is we're trying to find ways and do ways that just kind of set the stage for future collaboration amongst the three of us in terms of data analytics. So there's a lot of behind the scenes work, as you might imagine, in terms of how we collect data, how we store data, how we transfer data, how we protect data from confidentiality, and how we do the great science that Ralph and his team is doing and use that data as a live example. So very excited about this partnership, this 3-wire partnership, and truly propels NC State to the top of the list in terms of having the right people working side by side with our faculty on big issues. So let me end here with an update on the building. A lot of people like to talk about the building. I like to talk about the people and the science first. But let me review, if I can. This is an aerial shot of Centennial Campus with the plant science building kind of posed in here. And this is what the building will look like in its completion. You can see here, just to orient you, if you're familiar with Centennial Campus, you have Hunt Library here down in the upper left-hand corner of this slide. A very iconic building on Centennial Campus. You come up Partners Way here, and you'll see the plant science building here, almost on the corner, but not quite. You can see here the new engineering building. This shot was taken before that building was constructed. And so there would be a building now between our building and Hunt Library. And this is Oval Drive leading into the engineering oval complex here. Great location for our plant sciences building. So let's fast forward to about 3 weeks ago. This is a drone shot of the building here. You can see progress has greatly advanced. You can start to see definitely the shape of the building. If you can see my cursor, this is kind of where the front door will be opening up onto Oval Drive. That goes down to the oval, or excuse me, engineering oval here. The greenhouse complex that sits on top of the roof is right here. Across the street is the parking deck here that you see. It kind of looks part of the building, but it's not. It's across the street. But this right here, this area here will be the greenhouse. And then you can see obviously the kind of the Z-shaped plant science building taking shape here. Here's another shot from that parking deck. We're looking on kind of the, not quite the backside, but we're looking across the street on Partners Way. The first floor here that you see on the ground level is our the symposium room, auditorium room, catering kitchen will be right in this corner. And you can see again the 3rd, 4th, and 5th floor greenhouse going on top of this building here. And here is a kind of a cloudy shot, but this is a live shot taken about a week ago. This is the loading dock area on the back side of the building, but you can see the terracotta has been installed or being installed on this side of the building. The windows are in. The brick is, at least the brick staircase here on the left side is done on this building. So we are making great progress. I was out there yesterday, and somebody asked the head engineer how far along we were, and the answer was about 52%. So we're about halfway done. Pretty soon, the building is going to look like nothing's being done because all the work will kind of transfer from outside to inside. But we're excited about this. The project continues to be on time and on budget. And we're working through any of the little issues that come up as you build a building of this magnitude. There's always something that comes up, seems like daily, but I'm happy to say through great planning and great minds, we've really not had any obstacles that we haven't been able to overcome yet and keep us on time and on budget. So again, this fantastic plant sciences building coming along very nicely, and excited to show all of you this whenever we have the opportunity. The rendition of what it'll look like when it's all finished with people around it. Nice lawn, looking at the kind of the inside portion of that plant science building. Again, here on the right side is the main entrance, kind of looking over Centennial Campus off of Oval Drive there. On the left side, the bottom floor is that symposium or convocation room that can seat 140 and 150. And someday, hopefully someday soon, we will have one of these emerging research showcases in that large room, and all of us will be able to touch and feel and see the building by then. So that is my PSI update. I just wanted to kind of give you some of the highlights. If any of you need any more in-depth information on what's going on with the PSI, I am always available by Zoom or email or telephone to give me a call. So with that, I am going to turn it, I think, back over to Deborah or Jeff, and they will kind of tee up our 4 platform directors that have a short introductions about themselves and kind of their vision moving forward. Thank you very much.
Thank you, Steve. I'd be thrilled if you would actually introduce the 4 platforms for us, since they do come out of the PSI and you know them better than anyone.
I'd love to do that. I'm excited that we've got a great team in place. As I've mentioned, we've needed some science leadership, and we now have it with the 4 platform directors. So in not any particular order, let me tell you who they are. Leading our plant improvement platform is Dr. Sozzani, who's an associate professor in the Department of Plant and Microbial Biology. She's one of our CALS faculty members, very accomplished in her field. Leading our data-driven plant science platform is Dr. Cranos Williams. He is a professor in the Department of Electrical and Computer Engineering. Cranos is outside of CALS, which also excites me greatly because we talk about interdisciplinary efforts, and Cranos is supplying that view and that mind and that science aspect from an engineer's perspective and doing a great job. Our 3rd platform is the Resilient Ag System platform, led by Dr. Chris Reberg-Horton from our College of Ag and Life Sciences, Department of Crop and Soil Sciences. Chris is well renowned in his field and providing a lot of leadership in terms of agricultural resilience, sustainability, networking. He's got his fingers on a lot of things that is really providing a lot of input. And then last but not least, where we added the 4th platform, which also excites me, is our education and outreach platform. Dr. Hannah Burrack is professor, Department of Entomology and Plant Pathology, and again, has a great passion not only for student education and training and internships and making sure our students are well grounded in their training and getting ready to hit the field when they graduate, but also has a great passion of communicating science results to the field and also relaying back field issues and field questions that our faculty may need to address. So excited about Hannah joining as the 4th platform director here. So with that, I will turn it, whoever Jeff has keyed up to go first, I'll let them go.
I think that will be me, right, Jeff? I think we lost Jeff.
Yes, please. Ross, if you'll start us off.
Yep. And do you see slides or do you see the presentation?
We see slides.
Okay. It always happens. Okay. Okay. Here it is. I go in the darkness so that I only have one monitor. Very excited to see all familiar faces and familiar names. Very excited to be here today and to provide some opportunity. And now you're seeing the presentation, right?
We're still seeing slides if you want to put it on slideshow.
I did put it on slideshow, but I'll try to.
There we go. That's what we're looking for.
Yeah, it's just a little bit delayed. So as Steve said, the director for the plant improvement platform that
Ross,
Okay.
you mute.
I know my Zoom quitted and just restarted. Let me
Ross, would you like me to load your slides from here?
try one more time, and then
Okay.
in case yes, you will.
I'll be here for you on backup.
Okay. Plant improvement platform. So you're going to see at the bottom here 3 important aspects that are related to this platform. One is crop protection from biotic stress, and I'm going to walk you through some example. Plant adaptation to abiotic stress, again, some example there. And then agri-symbiotics, and you will see familiar research project coming up. What do I see in terms of these platform, in terms of the vision of these platforms? The plant improvement is about enhancing the characteristic of a plant species. Example here is giving rise to a new variety. There are different technology for crop innovation, and you will hear throughout the day, for example, gene editing from my very special colleagues, Anna Stepanova. What is enhance the characteristic? What we're going to look and what we're going to feel as a winning if we increase productivity. We have early pest and pathogen detection so that we can increase resistance, domestication of new crops with valuable traits, and of course, development of high diversity production system that will incorporate plant microbiomes that are really tailored for sustainable and improved production. And the vision here is, and the innovation is that drives the crop improvement is a true shift. And you will also see from, for example, the other platforms that there is a shift of research from description to prediction so that we can really move, for example, from genome-wide association study to genomic selection, or moving from phenotyping to phenomic selection. And here are represented, for example, the 4 Gri4-PSI that you heard from Steve's. So the platform has these 3 pillars, if not more, but the pillars that we are interested, and you probably have seen these already from a workshop that myself, Cranos, and Michael Kudinoff organized a couple of years ago in terms of identified crop traits associated with pest resistance, develop new sensor for early detection. And you also heard this is also part of the 3-way MOU with SAS and Microsoft. Development of biological or chemical fungicide. This is specifically one of the Gri4-PSI. And with the important co-creation of knowledge and working together, interconnecting with extension and research station to really improve integrated pest management strategies. The other, and here is just flying through because of 5 minutes, but I'm happy at any time to expand more. The other part of this platform is plant adaptation to abiotic stress. We all know we are ourselves, but importantly, plants are under permanent or periodic abiotic stress condition. You can also see on my Zoom background, weather because of water, climate, or soil fertility. And so as part of these platform is really identify crop cultivars, plant traits associated with enhanced performance in various conditions of a biotic stress, say drought or increase in temperature. The other aspect of this platform is really to develop tools and enabling technology for measuring this stress in a quantitative way, but also to be able to manipulate some specific aspects. So part of this is technology development like 3D bioprinting use in terms of effective plant regeneration, as well as state-of-the-art growth chambers that will be located in the PSI and have the capability to change up to 20 parameters, including CO2 and oxygen. And importantly, the third aspect of the plant improvement platform is agri-symbiotics. So plant symbiotic interaction with non-plant organism. And you're gonna see here on this side, the 3 projects under the CCRP funded grant from Novo Nordisk that is led by Amy Grandin, as well as other aspects that we hope, finger crossed, will be part of the adventure within the PSI, is this Science and Technology for Phosphorus Sustainability that is NSF Science Technology Center, which we will know around February if it will be awarded, and it will be part of the PSI direction, which is about developing inoculants and other technology like next generation of fertilizer that enhance yield potentials. And so you already heard from Steve, the North Carolina Plant Science Initiative has 4 directors, 4 platforms. Here are represented by this beautiful image that was made by one of our platform director, Anna Burrack. But what I really wanted to tell you here is that these platforms are interdependent, and we will work as a holistic unit. We're very connected, and there's really a team culture of connectivity among these 4 platforms. And importantly, these 4 platforms are interconnected and interdependent, because only among co-creation of knowledge, so working on problems in applied context, inviting non-stakeholder, non-academic stakeholder like these events, and seeking contextual rather than reductionist approach will really allow us to be impactful in the PSI. And as part of these co-creation of knowledge and these input from the get-go of important stakeholder is this network of network funded project that is accelerating integration of engineer and agricultural research using artificial intelligence that we were just recently awarded, and for which we will plan ongoing activities starting from these upcoming winter. And with that, I would say 5 minutes went by very fast, and I'm glad that I speak very fast. You know, I can even accelerate more, but is very enthusiastic to present a time frame and having a hero that points to where we're really going to look for game-changing research for plant improvement. Here are my information, and I'm happy to answer any question or have additional information that you need. So
thank you, Ross. Very much appreciated. Cranos, let's put you up next. Would you like to run from your machine, or would you like me to run the slides? And
I can run it. I can run it.
Okay, very good. Any questions that you have, please put them in the chat. We'll be collecting them later.
All right. And I'm assuming that you see the slide view as opposed to the presenter view.
It looks beautiful.
All right. So thank you all for giving me the opportunity to present today. Again, my name is Cranos Williams. I'm a professor in the Electrical and Computer Engineering Department, and I serve as the platform director of the Data-Driven Plant Sciences platform. Really the So as Steve and even Ross mentioned earlier, we have these 4 specific research platforms, and what I hope to be able to do within the 5 minutes that I have is to provide some level of insight into the vision and the underlying goals of the data-driven plant sciences research. Really, the underlying goal of this platform is to be able to expand the capacity and accelerate the ability to interpret agricultural data across the value chain. The overall platform vision is essentially to lead discovery, innovation, and translation in basic and applied plant sciences research through innovations in data management and integrated data analytics for plant sciences data. We want to be able to accomplish this by putting in place the structure, the IT structure, the laboratory infrastructure, and the computing infrastructure that is needed to acquire, process, and interpret agricultural data and facilitate innovation across the value chain. This goes from basic research and breeding strategies to crop production to decision support systems for stakeholders. Now, Steve gave, and Ross also gave a synopsis of the types of projects that are going to be under the Plant Sciences Initiative umbrella. And there's a common need essentially across many of these projects. Many of these projects are going to produce lots and lots of data, whether it's streaming data or experimental data. The expectation is these are going to be on the order of terabytes or more. And the likelihood is that many of these projects and potentially future projects have not identified a centralized way of efficiently managing and storing the data that will be acquired. And we find that it would be essential to be able to accelerate the discovery process to enable timely analysis of these data to be able to engender groundbreaking results. And thus, we're going to need to be able to not only leverage the common infrastructure within a university and current partnerships with external partners, but also enable a centralized service where we can enable efficient management and analysis of data. So thus, overall, we want to be able to address specific key barriers: lack of scalable storage and computing solutions for managing large amounts of data, poor accessibility amongst plant scientists and agricultural researchers to the computational tools and training needed to understand these data, and address the limited knowledge transfer between data scientists and those working in the agricultural arena. So thus, to be able to do that, this platform is really going to focus on the development and cultivation of 4 key priorities: sensor science and development for basic research and field applications, data management and cloud services, local and cloud computing architectures for integrative analytics, and training scenarios and training aspects for being able to train the current and next generation of plant science researchers in data sciences. More specifically, in terms of sensor science and development, we really focus on wanting to accelerate the development of next generation sensors and data acquisition platforms. And this will allow us to expand the type of agricultural data that can be collected by orders of magnitude, and also enable the real-time monitoring of plant systems across temporal and spatial scales. This means from the laboratory to the greenhouse, all the way to the field and research stations. In terms of data management and cloud services, we want to be able to enable strategic management of laboratory data and streaming data from sensors through the development of advanced database and tools and services that will enable agility within teams and increase the ability to collaborate across research groups inside and outside of the university. And to do this, we're going to need to be able to leverage and take advantage of strategic partnerships, particularly between, like Steve mentioned, between industries like SAS and Microsoft to be able to make this a possibility. In terms of local and cloud computing architectures, we want to be able to develop the advanced data analytics, such as distributed networks and grid computing, high performance computing, data visualization, machine learning, and scalable computing workflows to be able to understand and interpret heterogeneous agricultural data. This goes from the development of the algorithms needed to, machine learning algorithms needed to do this, and also enabling the cloud and edge computing infrastructure that will allow us to run those types of algorithms. And last but not least, we want to be able to train the next generation of plant science researchers. This means that we want to look towards increasing accessibility and a transfer of knowledge between engineers and data scientists and agricultural researchers, all in the effort of enabling opportunities to grow a diverse and interdisciplinary workforce that can then be sent out and facilitate services to our industry partners. So again, as Ross mentioned, we only had 5 minutes, so I just wanted to give you a highlight and an overview. This is my information. So as always, if you have questions, feel free to contact me, and I'll obviously be available for questions throughout the meeting and during the session at 5 today.
Thank you, Cranos. Appreciate that a lot. Chris Reberg-Horton, you're up next. Do you want to run slides or do you want me to run them for you?
If you don't mind running them, that'd be great.
I don't. I even have them loaded up.
I can barely walk and chew gum, so.
Oh, give yourself a little more credit. I'll bet you could do both. Hang on, I've got it here somewhere.
I can pull it up if it's trouble finding.
No, it's here. It's just a matter of there's a lot open on the screen, as you might imagine.
It's all right.
Brazilian ag. There we are, front and center. Now we got it.
All right, yeah, that's me. All right, well, good afternoon, everyone.
Is it showing?
Yes,
Oh.
I'm not in slideshow mode yet, but I've got it. So, oh, perfect.
Yep, I'm going to switch it.
How's that? We'll see. Yeah, looks great. Thanks, Deborah. Oh, it's back off.
Now
Let me go. You're on.
That wasn't good.
I'm sorry. I'm making life more complicated here. Hold on a second. Let me do it. No problem. You see it now?
Yeah. I wonder what happened. Technology happened.
That's right. Yes. It only happens during technological presentations that technology doesn't work. Let me see if I can get it. There we go. All right. I want to step back just a second. I know 5 minutes. You don't have a lot of time to step back, but I like the little historical context for what we're trying to do with PSI around resilient agriculture. And start with the question first now is where are we at right now in agriculture? Are we really a part of the industrial economy, like manufacturing, or are we becoming a part of the knowledge economy? And so I'll argue to you first that we've been a part of the industrial economy for quite a while, for the last 100 years at least. And when I say industrial agriculture, industrial economy, I don't mean it like an insult. Sometimes we see it in the press used as though it's an insult against large farming. And I don't mean that any way. I mean it as an analogy to the industrialization process that hit all sectors of the economy, from manufacturing to everything. And if we look at how that impacted agriculture, we see a tremendous gain. We have farm machinery increasing in size, number of farmers per acre decreasing, increasing specialization, just like we saw in all sectors of the economy. And that gave us the incredible productivity gains in agriculture that we have seen over this time. And so, you know, and I oftentimes view that process as an inevitable and necessary one. I mean, we can't run a modern economy with the majority of folks engaged in agricultural enterprise, which is what would have been present over 100 years ago. Majority of people involved in agriculture. Now we're down to a few percentage of the population involved in it, and yet producing more production than ever. But we also have to recognize that there's a downside to that, and what have we lost as a part of that? We've lost a tremendous amount of biological diversity on the farms. And I'm not talking about just in terms of crops. Certainly there's been crop specialization. Each farm has fewer crops on it. But we've also seen that in loss of habitat. Here in the Southeast, near and dear to my heart is the loss of quails. But we've seen that in a lot of the complexity of the farmscape has been reduced. And it's been reduced because we needed to accommodate larger and larger machinery. And that loss of resiliency is coming at a time when our climatic pattern here is shifting, particularly in the Southeast. We've seen that in the last few years here in North Carolina, and our ability to adapt to that has been impaired. You know, so just to highlight another thing, and people say this again across all sectors of the economy, that one of the things that makes an industrial economy possible is that we have to simplify the production floor in a very real way. And so we've had to simplify each farm in order to achieve those incredible scales of efficiency that we have been able to achieve. But I think we're at a point of transition, and that's the overall point we make here. And I think that's what the PSI as a whole is recognizing, is that we are on the verge of a revolution here that is no less profound than the Green Revolution. So if you look at what's going on with what Cranos just talked about with big data, we look at artificial intelligence, if we look at the coming of robotics, we are on the verge of profound change that we haven't seen in many decades. And my interest is, what can we do with that change that's coming to achieve some resiliency? So first, let's think about what it means to be a member of the knowledge economy. One thing that's enabling in agriculture, again, is the shifting, the sensors, the smart machines, the artificial intelligence are already becoming active on growers. And we're able to use that to regain some of the knowledge about each individual square inch of farmland that we have lost with the loss of the number of farmers engaged in that process. So, you know, a lot of the growers I work with manage many thousands of acres over my career. And so they're managing these huge swaths of territory. If they look back 2 generations on their farm, their grandparents might have only been on the hundreds of acre scale. And so the number of, you know, farmer neurons per acre has gone down. And so this artificial intelligence and big data allow us to replace some of that lost knowledge. The other thing to point out is that complexity is now going to be able to be back in our management plans in a real way. And so adaptive management, there's a lot of strategies for resiliency that have been proposed over the past few decades that have just not been practical. And I think a lot of that is becoming practical with the availability of all this technology. Robotics is another one that I think is going to be a key part of this transformation. Robotics allow us to farm on different sized fields, different shaped fields than we're able to do. Well, I work in corn, soybeans, wheat, and so, you know, a lot of things are our logistics are scaled around a 30-foot head. Parts of the Midwest, it's scaled around a 60-foot head. So, you know, we are at a disadvantage here in the Southeast because we can't, you know, we've not got a lot of territory where 60-foot heads can run. We've got a few counties where they're good, but a lot of places where that's just too big of a head for us. But if you look at what's going on in robotics, those machines are substantially smaller than the farm machines that we have seen traditionally. That's going to allow us to get diversity back in that landscape. I like to point out that, you know, in the Southeast here, we tore out our hedgerows, not because we thought the land underneath the hedgerows was particularly attractive for farming it. It's just because we needed to get that large equipment in there. Oftentimes the hedgerows were planted on wet bottoms, they were planted on sandy ridges. The farmers in the past knew that wasn't good land, but we couldn't run our equipment around with all those hedgerows in our way. You put robots on the landscape and we can start to look at that type of diversity coming back. The other thing to point out is that, you know, the consumer has shifted a lot in the last few decades. And so farmers no longer, consumers no longer want just food out of the agricultural system. They're seeking other things. They're oftentimes seeking environmental claims. We've seen emerging carbon markets, soil health claims, habitat claims being viable in the marketplace now. We have a number of companies now that are incentivizing growers to be a part of those claims. I point out, 5 minutes to explore that, but we've got several companies operating here in North Carolina now that are working with growers to make those claims. Smithfield and Indigo Ag both have active programs for encouraging farmers to live up to environmental claims made by their products. And so then I'll end with, you know, I think the other thing that this technology is making possible is that the farms are going to become part of the land grant experimental system now. I've spent most of my career doing my experiments on the experiment stations and then doing my extension on farm. But now we're going to see different pipelines possible where more of our experimentation will be possible on the farms themselves, and experiment stations will be test beds that we can use for all these new technologies as they roll out to the farms. I think I've shot 5 minutes, so I better stop there.
Wonderful. Thank you, Chris. And Hannah's up and she's already started sharing, so marvelous.
All right, so I get to wrap things up. That's the order we generally go in. And thank you again for the invitation to join everyone this afternoon. For those of you who don't know me, I'm Hannah Burrack. I'm an entomologist by training and practice. I work in specialty crop systems, primarily doing applied research activities. But the role that I'm taking on with respect to the PSI is leading the education and outreach platform. And this really is the piece that ties all of these other platforms together and will fulfill the promise that we're making with PSI, that the cutting edge, innovative science that's being conducted will be delivered to train the next generation of innovators, as well as impact and be utilized by our target stakeholders. And we take the idea of stakeholders very expansively. And so, as I said, we're encompassing the education and outreach component here. And I keep my slides very minimal because I want you to really focus on how we are going to embrace these activities within PSI. The ethos of all the projects that are currently underway through the Grip for PSI program, as well as other affiliated projects that are emerging, is that they will be transdisciplinary and they will involve translational work. But in order to make that happen, we need a concerted and focused effort. So the vision of this platform is that the science we conduct at PSI will enable education and extension innovation. So we will do new things in the realm of agriculture and scientific education and extension. We'll enhance our workforce, both on farm and with allied industries. And that will translate to increasing our stakeholder capacity and adoption of the science that's done at PSI. So we see doing this in several ways. We obviously want our scientists who are engaged at PSI to have a real and tangible connection with our stakeholders. We want the conversation when science is being conducted and delivered to be two-way. And again, we take an expansive view of who our stakeholders are. Those are growers, those are also extension agents, those are allied ag industry partners, and those are our students at all levels, Ag Institute, undergraduate, and graduate. We have a really exciting opportunity here to dramatically increase the capacity of those stakeholder audiences. In 5 to 10 years from now, our extension agents, for example, are not just going to be asked, what pesticide do I utilize to control this organism? Or what fertilizer should I use when I plant a given crop? They're also going to be asked to help growers decide, what data management platform do I utilize? What sensor technologies are going to make the most sense in my operation? And we are positioned to be able to give them the ability to effectively make those recommendations and be the new authority on the modern edge of agriculture innovation. We also have an exciting opportunity to integrate more fully with our research station partners. This is efforts that have already been underway, but through work being done at PSI, we will be able to more effectively mirror the modern farm with our research stations and be able to leverage the data that are being gathered in ways we haven't been able to in the past. I'm particularly excited about our ability to contribute to graduate training, undergraduate training, and Ag Institute training. We have the ability to house interns in the PSI, to physically house students through the course of their program, as well as to make connections with end users for each of those audiences. And we see doing this through short-term internships, ideally longer-term traineeships that are housed at PSI, where we can bring in industry partners to utilize this space, as well as have our students experience working in those environments. And then envisioning ways of training scientists who are ready to move on and lead their own programs through perhaps translational postdoctoral opportunities that would provide focused training in communications, mentorship, extension, or technology transfer in ways that our students typically don't get access to in their undergraduate or graduate programs. So really innovating and building the capacity of all of those groups. I'm particularly excited to be here this afternoon because the folks sitting in this meeting are some of the folks who are best positioned to help support and engage in these activities. So I'm looking forward to continuing the conversation as we move forward today.
Thank you, Hannah. Really appreciate that. We have one comment and one question in the chat. So let's take those really quickly. The comment comes from Craig Yencho, and it's for Cranos. Craig says, you're right on with limited knowledge transfer between data scientists and those working in the field. If we can make this connection, it will be a major stride forward. Cranos, do you want to, it's a comment, not a question, but do you want to respond?
I completely agree. I think that one of the things that I found in terms of interdisciplinary projects is that the sharing of information really accelerates the spread of information and the interpretation and long-term innovation associated with those projects. And if we can identify effective ways of doing that, I think that we will make tremendous strides forward. So I do nothing but wholeheartedly agree.
Thank you, Cranos. And we have a question from Suzanne Kemtrup, and actually also for Cranos. Cranos, you spoke about data challenges for plant research. Given that at NC State we have projects in field sensor development, can you talk about any efforts to develop novel network solutions for data upload in remote or rural field settings? Excuse me.
That's a good question. And I think that that's something that is going to be a significant challenge, whether it's what Chris was referring to in terms of actually working with and doing experiments on the farms themselves, or even interacting with some of the research stations that may not have the type of bandwidth and functionality that you would want them to have. So I think some of the things that we've been trying to explore are opportunities for edge computing. So being able to perform various types of analyses and machine learning approaches closer to the sensor. So being able to develop algorithms and have machines that will allow you to do that. And then that will make you provide opportunities to be less reliant on, for example, on the cloud. And then there are even some other aspects that Chris has talked about in prior meetings in terms of utilizing other types of bandwidth or spectral bands to be able to communicate beyond just the cellular bands, or even things associated with high throughput internet. So, identifying and looking at, those as potential alternative solutions may be opportunities for addressing some of the problems that are in more of the rural areas.
That's great. Thanks, Cranos. In order to keep us on schedule, you know how I love my agendas. There is a comment from Kelly. We'll come back to that hopefully at the very end. I'd like to turn it over to Dinah Schuster, please. Dinah.
Thanks, Deborah, and good afternoon, everyone, and welcome. Thank you for being here today. I appreciate the opportunity to introduce myself. I am we have very fancy titles in academia. I am the Senior Director of Development for the Plant Sciences Initiative. That translates into I'm one of the lead fundraisers for the PSI, not only the building, but as well as the programs. And so delighted to hear our platform directors share their initiatives and give an overview of what they're doing, because myself, along with a very large team at CALS, we're very excited to help with all of that. In addition to that, I wear another hat as the Executive Director for the Research Foundation Board. And I'm delighted to see that we have several members of the Research Board participating today. And I thank you all for being here. I think what's exciting for all of us is that the Emerging Research Showcase is a brainchild of the Research Foundation. And so, again, this is meaningful for us. So I really just want to, as I was looking through all of the participants, I see that there's a lot of companies as well as some commodity groups who have always supported us, and we appreciate that, and have supported us, especially with the PSI. There's really too many for me to name, and I want to just remind you all, as you're sitting today listening to all of these presentations, that many of you already have a sponsored research collaboration with CALS. But I'd like to tell you that several of you all have also complemented that partnership by making gifts. And I'd like you to think about some of those opportunities. I think Hannah actually touched on one of those. These gifts are including graduate students, faculties, and programs. And CERSA, which is one of our really most beloved programs coming out of the PSI right now, is supported by many of you as well. So I'd like for you all to think holistically about your support at CALS, not just the sponsored research, but other ways that you can have really good impact in supporting the work that we do. And I would say that if you're curious about what some of that looks like, please send me a chat. I'd love to follow up with you. And again, enjoy the rest of the afternoon. This is really a lot of fun. And I will now turn it back over to Deborah, who does like a time, staying on time. And so I hope I got you back a few minutes. So thank you so much, everyone.
Thanks, Dinah. So I'm going to do a quick screen share. Do you by any chance actually see my slides? Somebody, Jeff, do you see my slides?
Yes.
Thank you. Okay.
Yes.
All right. So I'm going to just, I suppose it just gave you, hang on, let me switch the setting. You should see the slide, not the presenter mode. And I don't, and it's almost not worth it because I have very few slides. I just want to talk to you for a minute about partnership, because my role is partnership development for the College of Ag and Life Sciences. And at the end of the day, we all love a gift. And if you want to come into the college with a gift, then Dinah is the person that you need to speak to. But if you want to develop a research collaboration, then I hope you'll work with me, because my job is to really bring to life the vision that Steve Lommel gave me the first day I walked into the office, which is help me build deep and enduring relationships with our industry partners. Not to belabor the point, but we are the College of Ag and Life Sciences and Friends, and we are open for business. I hope you can see that in our invention disclosures, our patents filed and issued, our licenses, and our startup companies. We do agree and embrace the university's think and do mission. And so we do want you to partner with us. And as you're listening to the 5 brief presentations, faculty briefs that come up next, I hope you'll think about how that partnership can work. It can be as small or as easy as a letter of support for a grant proposal that somebody's putting together. Maybe there's an opportunity to join a research team. Of course, give a gift or to sponsor a research project. And we have a number of different flavors of research sponsorship that we can discuss later. I don't want to put the cart ahead of the horse here. And so watch me be really brief. And now hand it over, if I could possibly find my screen again. Give me a second. At this point, I would like to turn it over to Sierra Young to get us started on the research briefs. And Sierra, do you want to share your? I have to stop share. That's what the problem is. Ta-da! Sierra, do you want me to run it from here, or do you want to run?
I can do it.
Take it.
Can you see my slides?
We can.
Great. Well, thank you for giving me the opportunity to speak today. My name is Sierra Young. I am an assistant professor in the and agricultural engineering department. And my work focuses primarily on the development of sensing technologies and robotics. So this is the core of what myself and my research group focuses on, and this does cross boundaries with data analytics and really obtaining useful information from these technologies and integrating that information into decision support tools, but really the emphasis for my research interests focus on technology and sensor development. So the project that I'm going to discuss today focuses on soil moisture. And so soil moisture, as I'm sure many of us know, is an extremely important parameter that should be considered and estimated in quite a wide variety of hydrologic and agricultural applications, in particular looking at soil moisture and temperature estimates in that first bit of topsoil. So soil moisture, understanding of this throughout fields is important for things like effective irrigation management strategies necessary for field preparation and planting decisions. Also, of course, it impacts crop growth, transpiration, and also affects ecosystem respiration. So there's quite a bit of applications in which having accurate topsoil moisture estimates are really valuable. And so valuable, in fact, that there are, of course, now global efforts focused on mapping and monitoring soil moisture at, across the global scale. So this is an example of soil moisture across the root zone from the soil moisture and ocean salinity satellite sensor. Of course, this is not a high enough resolution to make meaningful decisions at the farm or field level, but I'm interested in how can we create similar maps that are readily and accessible and available to growers using low-cost technologies at really high spatial resolutions. So of course, remote sensing using unpiloted aerial systems has emerged as a critically important tool to generate high-resolution soil moisture maps. And so this is achieved through a variety of ways using sensors such as thermal as well as multispectral imagery, taking a variety of modeling approaches such as using exponential, thermal inertial, now more recently machine learning models to relate these reflectance and temperature values that we obtain from these unpiloted systems to ultimately estimating soil moisture. But it's been shown quite a bit that there are a lot of these modeling approaches tend to be field specific. Perhaps they don't necessarily generalize well if you develop a model in this context to a wide variety of contexts. And there's a variety of reasons for this. Things such as soil moisture, composition, compaction, porosity, even things such as irrigation patterns and tracks left from agricultural machinery can all affect how we estimate soil moisture when using images and looking at that topsoil. And so one way to remediate these problems is to collect ground truth data. So we collect remotely sensed information and come in, and whether it's through in situ sensor networks or perhaps using a handheld soil moisture probe, collecting some ground truth data to help validate and correct for some of these field-specific properties that may affect modeling. And so I do want to also note that there are some UAS technologies that leverage passive microwave radiometers and other types of microwave tools to get accurate soil moisture estimates, perhaps without this, but those are generally still quite expensive and not necessarily accessible to a grower or producer who may need this, this tool. So I'm quite interested in how can we perhaps even augment consumer platforms using low-cost sensors to generate these accurate soil moisture maps. And so there are ongoing efforts to do this autonomously through small ground robots for mapping and measuring soil characteristics. So generally this approach includes some type of autonomous system capable of drilling or sensor insertion to obtain those soil moisture characteristics from the ground and doing this autonomously. But I have been thinking recently that there's quite a largely untapped resource in UAVs that give us the potential to interact with the remote environment, and they have much more increased mobility compared to ground vehicles. So this is just an example of some more recent, really within the last decade, we've seen quite a bit of advancement in these so-called manipulating UAVs. That now we're not just looking from a bird's eye view, we can actually go physically touch, sense, grasp, probe, deploy, and retrieve objects with these flying systems. And this is largely due to advances in vehicle control and dynamics. And so as an example, I've in the past developed a system capable of grasping and manipulation. There's also sampling systems and forestry and a wide range of applications. So using this as motivation, how we can push these technologies farther, the goal of an ongoing project I have is to develop a single system capable of remote mapping as well as in situ validation using a low-cost UAV. So the thought behind this project is that we can take some of these off-the-shelf consumer platforms and sensors currently being used to estimate soil moisture, and I'll equip that platform with a payload mechanism that can actually land and sample the soil. So we have this platform that is collecting this remotely sensed data, capturing that variability within the field, and also then determining where the most optimal sampling locations may be, and going to those locations and obtaining those in situ validation points. And so what this project aims to do is really combine and integrate some of that ground-based soil moisture measurement in the ground with cutting-edge advances in T-spectral remote sensing to have a autonomous workflow to generate accurate soil moisture maps at the field level. And this is also important because understanding where to take those validation points to capture the within field variability is really important. So some current progress that has been made, I have a really great graduate student who has been able to essentially develop a proof of concept system that's capable of drilling and sensor insertion to obtain a point measurement. And so we have it here on this portable frame. The frame weighs about the same as our UAV, so we're working on transitioning this now to a larger platform. But we've shown that with a relatively lightweight platform and some precise controls that we can actually drill and insert a sensor, do this at a couple different locations within the field. And so now we're working towards repeated field testing and evaluation to understand the reliability of such a platform and begin to integrate these data with some remotely sensed data we collected earlier this summer. And so ultimately the next steps of this work are to have the remotely sensed images, but also add another layer that I think perhaps gets left, is that to capture some of the small variability within surface conditions that may also affect the soil moisture measurements, such as microtopography and soil color and ground cover, even shadows, and be able to obtain this information as the UAV lands and then classify that information. So now we have remotely sensed data and we have ground cover classifications and information from where the discrete points were taken, and then we also have those discrete measurements. And all of the goal of this is to have this entire workflow be completed autonomously. And so really we see a wide range of potential applications for such a tool. An interesting application is equipment and field safety, so potentially scouting out for wet spots to prevent large agricultural machines from getting stuck, essentially. Also, of course, incorporating soil moisture as additional layers in precision agriculture applications, and also using its information to inform crop and climate modeling. So with that, really to support and kind of accelerate the work of this project, I'm seeking potential industry partners who may want to collaborate, but also support through written letters as I move forward with proposal development for this project. And I think that's about 10 minutes, so I'll stop there. Thanks.
Thank you, Sierra. I haven't seen any questions come through for Sierra in the chat. Are there anyone wants to ask anything? And I think Sierra's going to stick around for the networking at the end, right?
Yes, I will be there. A bit late, but I will be there.
Okay. And Suzanne, I see that you have a question rather than typing it. Why don't you go ahead and just ask it?
That's a great idea. Yeah, I had a question. You've got all these soil samples now. Have you thought about microbial applications?
Oh, that's really interesting. So I have not, but I think there's definitely an opportunity to, having collected all of these, to do subsequent analyses. So that would definitely be a really interesting component to kind of add on to the mapping and validation components of this. Is, you know, we have this platform capable of obtaining these measurements and perhaps collecting small samples as to, yeah, that would be a really nice addition, I think, is to perform subsequent analyses on those samples as well.
Can I ask my question, Deborah, instead of typing it?
Yes, I unmute myself. Go ahead, Karina.
Sierra, fantastic presentation. Are there challenges associated with variation? And what I mean is by variation in terms of being able to repeatedly get to the same spot and sample in the same way over time? And do you think that that has any implications on not only the downstream interpretation, but also the push to develop, you know, other advanced algorithms for control and manipulation?
So that's a really good question. For our application, we're focused on looking at at least at this point in the project, repeatability and reliability in terms of I guess the range of soil types and moistures that we can actually essentially probe and sample with this prototype. We haven't addressed the problem of going back to the exact same location. Although I imagine with some of the, really comes down to vehicle controls and automation, if you can achieve centimeter level precision navigation in the field, which we can with precision GPS technologies, I don't foresee a significant problem going back to sample perhaps the same location over time throughout a season to envision how that changes. But I think that would be a really interesting test once this is fully developed to, you know, do the same type of mapping experiment in the same location over time and see what that looks like. So
fantastic. Thank you so much.
Thanks.
Sierra, we actually have two more in the chat. One from Kelly. The question is, how much does the soil drone cost currently, and how many collaborating farms are you looking for?
Thanks. So the first question, how much does it cost? Right now, the payload is maybe only a couple $100s, and then the platform itself is approximately, I think it's between $5,000 and $6,000. It's one of the larger platforms by DJI. We are hopefully looking to scale this prototype down such that it can fit on smaller, lower cost platforms as a long-term goal of this work. And really for right now, as we're in the prototyping stage, a handful of farms would be really great to be able to test this on different soil types and textures and obtain different maps and different conditions. So really, we're just looking for places to test this out right now.
Great, thank you. And one more in the chat from Ramya. I was wondering what kinds of machine learning methods you're integrating in your technology, if you're integrating them at all.
Sure, so that's a good question. So right now we're just simply exploring statistical machine learning methods. We're looking at models such as random forest and SVM just to see how we can use the reflectance data in addition to thermal data as predictor variables. So right now we're focused mostly on how we can incorporate the in situ validation measurements into those models, and then hopefully ultimately once we know that the information is useful, be able to explore multiple modeling approaches as well.
Thank you, Sierra. Marvelous presentation. If you could unshare your screen. I never knew that was a verb. Carlos, I think you're up next. Carlos, are you muted maybe? Carlos, I see your slides, but I don't hear your voice.
Can you hear me now?
Yes.
Oh yeah, it happens sometimes. I don't know why.
But okay, and we have slides coming.
Cancel this. All right, thank you. Sorry for, yes, can you hear me?
Yes, we can. Thank you.
Okay. You scared me now. Back to plants. I guess we haven't seen many plants. This is a plant science presentation. So here's a bunch of colorful crops. We work in 40 different species at NC State. We have 27 breeders, and we work in improvement of 47 different species with considerable impact, not only at the state level, but also regional and also global impact. In some of these crops, which out of those 40s, is a great majority of them can be classified as specialty crops, and that's the topic of this presentation. is that based on that impact that we have had through the years in developing improved materials, we are now building a platform that incorporates a lot of basic research pillars to get an exponential improvement in the future and to make ground for future partnerships, as well as train our future scientists and professionals in the field, okay? I'm gonna talk about 3 fields as part of that platform, 3 areas as part of that platform. Here is sort of the concept of the platform is to work in improving crops through breeding systems and studying the fundamentals that can solve compelling problems and bring up new opportunities for these specialty crops. And of course, when we talk about specialty crops, it doesn't mean that the science and the genetics we develop for those crops is not applicable to other crops, okay? But it happens that NC State has built up a significant strength in specialty crops due to the diversity of our state, diversity of crops and environments in our state. So the 2 basic pillars for our platform is the areas in plant biology, like functional genomics, bioinformatics, nutritional genomics, and molecular physiology. And the other area is the area of biotechnology through gene editing and transformation. And as I said, I'm going to be talking about 3 aspects of our platform. The first one is what we are aiming at developing gene editing methods that are species and genotype agnostic, I would say. When we talk about CRISPR-Cas9, we have to deliver the protein through transformation systems. And most of you know that a lot of the species are very recalcitrant to transformation. And even those that are amenable to transformation, very few genotypes are regularly used. And that creates a significant problem for some of our crops, which are vegetatively propagated, because we cannot just transform one genotype and think about transferring that edit to other genotypes through backcrossing. That's not possible for us. Okay? So we are aiming at developing this technology that will allow us to transform and edit several genotypes within species, okay? The other aspect is that we're looking at non-GM type of technology. In sexually propagated species, the ones that are propagated by seeds, usually you can shrug off the GM part of the editing system. That's not the case for vegetatively propagated species. So we do need to look at non-GM systems if you want to edit, for example, sweet potatoes for Eastern Africa, or sweet potatoes for the export market that will go to Europe, for example, okay? So among the potential avenues that we have for that involve magnetic particles blended with pollen, nanotubes. But one of the areas that Dr. Wushan Liu, who is in charge of this project, is looking very closely is injecting agrobacterium into mature tissues with the possibility of regenerating tissues that carry the gene edits without carrying the GM part, okay? And we have submitted a proposal to FFR and we're waiting for a response, but Dr. Liu is pressing on with this research, basically looking at injection in mature plants, in intact root systems, in potato as a model plant, because there has been some promising results, and also extending that to other species, specialty crop species like lettuce, sweet potato, and tomato. So Wushan Liu is the person that you guys can contact for this type of information, and he's the one that's going to answer the questions about this particular part. The other part is the plant transformation lab. We are boosting up our capacity for the plant transformation lab. We have recently hired a new director, Dr. Kedong Da, who is also here in this audience, and we are aiming at increasing the work that we do to understand better the physiology of different genes and how to manipulate them, okay? Focusing mainly in yield, disease resistance, stress, nutritional components, mainly in specialty crops, okay? Dr. Dao also is specialized in double haploid production. So there's a lot of possibilities there to team up to enhance double haploid productions in several specialty crop species. Okay, so here's sort of a menu of the different technologies that his lab is working on. Finally, there's an international component to our specialty crop platform. This component is led by Craig Yenshaw, and is applying the area of genomics for the improvement of sweet potatoes, which are vegetatively propagated polyploid species. So there's a lot of genomic tools that are being developed within this project that has broad applicability to other similar crops, which are specialty crops. A lot of these tools have been, there's a lot of progress in genomic tools for crops like corn and soybeans, but they're not broadly applicable to crops that are highly heterozygous, vegetatively propagated, and polyploids. Okay, so also as part of that project, there's a new genotyping platform that's being currently under patenting. It's called SCIP, which is very applicable not only to specialty crops, but any type of crops that is part of this research, okay? As well as we are collaborating with other institutions for management of databases related to breeding of these types of species and high throughput phenotyping, okay? So our goal is to improve productivity, profitability at the farm level, also nutritional and environmental sustainability through the work that we do in specialty crops, okay? And as I said, we have a great impact from the varietal point of view. And now we're developing enabling technologies through different areas like genotype independent non-GM gene editing, plant transformation, new genotyping platform like OMSIC, statistical genetics applied to polyploid and vegetatively propagated crops, nutritional genetics with a group in Kannapolis, and also the area of phenomics. Okay, so our specialty crop improvement platform is generating great technology with potential to benefit all crops, as I said. Okay, it happens that we are very strong in specialty crops. Okay. It will allow us to better train the future generations of scientists and help alleviate production and nutritional problems, as well as support the economy of our state and our region. So we are looking for partners who want to be part of this endeavor and contribute to not only solving the most pressing problems in these crops, but also in looking at unexplored opportunities in specialty crops. Our state, our region is particularly well positioned for exploring these opportunities with specialty crops, and we hope to generate, together with different institutions, a lot of support technology that will enable our region to be that. I think that's all I have, Deborah. This is my contact information. I imagine you guys are going to have copies of this presentation. So here, if you want to contact me, I'm the coordinator for this platform, and I'm also the director of the Plant Breeding Consortium here at NC State. Feel free to contact me, please. Thank you, Deborah.
Carlos, thank you so much. We already have a question in the chat. This comes from Bao-Chun Lee. Have you tried the magnetic nanotube approach using pollen tubes as targets for plant transformation? And if so, what is the result?
And I hope that Wushan is part of the audience and he's going to answer that question.
Wushan?
Yes, we are doing that with tomato, and we are trying to use that method to deliver the Cas9 DNA and also protein into the tomato pollen, and then hand pollinate the stigma. So far we got some positive results. We can see some generating seedlings which contain the reported gene expression, and also we are working with stable delivered plants. So far we got a few plants which show the positive results. Thank you. That's a very good question.
Are there other questions for Carlos or the specialty crop team? And I believe there at least some of them will be available for the networking session as well. Seeing nothing come through.
Good.
Carlos, I'm going to ask you to
Yes,
unshare your screen.
Stop sharing. Yes, I did.
And we have Colleen Doherty up next. And Colleen, are you going to run from your machine, or would you like me to run from mine?
Run from mine.
Thank you. Colleen, we can see a mountain, but we can't hear you.
See screens?
Now we see screens.
Okay, sorry, it was taking a minute there.
It will. Thanks.
Okay, so thank you very much. I am here today to tell you about the secret life of plants at night and how time management affects their ability to respond to stress. So we're told from an old adage that you can't rely on anything except for death and taxes. And I would like to say that there's a more fundamental component to that, and that's if the sun doesn't rise in the east every morning, then you won't really care too much about your taxes, because that's a very consistent recurring event that happens every single day about the same time the sun rises in the east. And most organisms on Earth have adapted their life cycle and all of their activities around this consistent 24-hour life cycle. And plants are no exception. So if we look at plants, they take advantage of these recurring cycles and these recurring rhythms, and they modulate their activities around these predictably recurring events. So for example, in some of the figures here, the leaf movement where the leaves are moving up and down, that's an indicator that either water turgor in the top plant is taking up at different times of day, or in the bottom plant, that the actual growth is varying depending on the time of day. And if you look at the pumpkin up on top, you see it kind of swells up every night and goes down every morning, or stops growing every morning and swells up only at night. That's an allocation between source and sink. And that it also is regulated by the plant circadian clock, so that it's only allocating those resources when it knows it has them into them. And then finally, my favorite here, this is the sunflower plant, and it has this beautiful heliotropism where it follows the sun across the sky. But what's most fascinating about that is if you look at night, it reorients back to the east to prepare and anticipate for the very first rays of light. And so it's there ready to capture. And that anticipation is a hallmark of the circadian clock, which is present in all plants we've examined. And it's not just at the physiological level that those leaves are there ready to capture the first rays of light coming from the east, but at a biochemical level, this is happening too. So the very first photon that hits the plant hits a completely ready photosystem. The photosynthetic enzymes are all up and ready to run. And this is true at the gene expression level, at the protein level, at the metabolism level. And what this means is that there's this temporal regulation throughout the plant at all of these levels. And so this is just some of our data from field-grown rice plants. And here we've shown all detectable transcripts. So every transcript in the rice panicle that you can measure, and we've bin it by the time of day. So each row is a transcript, and then each column here is a different time of day. And so you can see that these transcripts up here are transcripts that peak in the morning and aren't highly expressed throughout the rest of the day, while these other transcripts here peak in the middle of the day, these transcripts here peak late in the night. And so the key point from this is that at any snapshot in time, if you look here in the morning or you look here at night, the transcriptional landscape is highly varied. And so an experiment done at this time or a stress that happens at this time is going to essentially happen biochemically to a completely different plant. The plant at this time of day is very different than the plant at this time of day. And this organization means that plants are really exquisitely timed to both their environment, both daily and seasonally. And it may not seem obvious how a clock controls seasonal responses, but the clock is fundamental for controlling developmental transitions like when to flower, because if you need to measure that the days are getting shorter or longer, you need to know what a 24-hour period is. So the bottom line of all this is that time regulates almost all activities in plants. from biotic stresses to abiotic stresses to when they take up water. And so plants have really been optimized through breeding and through evolution, in the case of natural plants, to maximize their use of time, and everything is properly timed to have the most efficient timing. The problem with that is that times are changing. So things that we've bred for in the past, to have flowers that open as soon as it's warm enough to open so that you get maximum productivity of the fruit, now has problem with flowers that are opening as soon as it's warm enough, but now the temperature is changing. And so these biochemical pathways that have really been bred through time and selected for successful decision-making have been disrupted because the time is changing. And so my lab is really interested in how these patterns and these changes in these patterns impact the crops. And there's three areas we focus on. One is the northernward movement of growing zones, or poleward movement, both in the north and the south, and that these warmer seasons are now affecting plants that are in different photo periods. We're also interested in earlier springs, the fact that springs are trending early and earlier. But the one that we spend most of our time on is the asymmetric warming of daily temperatures. So what that means is that nights are warming faster than days. So while global climate, the temperature is increasing both locally and globally around the world, this is shown here by the daily maximum temperature. What's actually happening because of the boundary layer effects in the Earth's atmosphere is that nights are warming faster than days. So this is the daily temperature maximum. This is the daily temperature minimum. And so what happens is this daily temperature range, the difference between day and night temperature, which is about 10 degrees in North Carolina, it's pretty consistent all year round. This daily temperature range, which is essential for plants to set their clock, to set a lot of their biochemical activities, is shrinking. And so that is very disruptive to crops. So rice has kind of become this like model system for warm nighttime temperatures, and that's where we've done most of our work. And we see that along with others, that really a very small increase in nighttime temperatures can have devastating effects on yield. And one underappreciated aspect is this effect on grain quality. And again, that comes from that clock regulation of source to sink distribution. And so the bottom line is, it's not really the heat, it's the timing of the heat that's the problem. And so this is showing that this is true not just for rice, which has kind of become the model, but as a very fundamental aspect of plant physiology, the time that a stress happens really makes a difference. So these are Arabidopsis, these are lots of seedlings on a plate, it's just zoomed out really far. And so depending on when we give that experiment, if we do the experiment at dawn, midday, dusk, or midnight, if you look at the plants here in these last two rows where they're either just taken straight from their comfortable chamber to a sudden heat shock, or they first get a warning that the heat shock is coming and then they're moved, you can see there's variation. At dawn, they're very sensitive, both with or without the warning. At midday, they can survive better. In the late evening, they're very good and they can survive very well. And at midnight, it comes back to being very similar to midday. They don't seem to tell much difference whether they get the warning or not. And so the bottom point of this is that it depends on what time of day a stress happens. And that's really not surprising given this underlying variation I already told you about. If we look at any one of these genes here in any of these rows, there is a variation in when it's expressed. It has a time when it's higher expressed and a time when it's lower expressed. And therefore, whenever a stress happens, there's probably going to be a difference response. What surprised us is the magnitude of that difference. So this is one classic heat response gene. So here, this gene in the control conditions in the morning is not highly expressed. Controlled conditions in the evening here is not highly expressed. If we give a heat shock in the morning, this gene gets induced more than 1,000-fold. But in the evening, don't see much change at all. And this is true for most of the classic heat shock genes. Most classic heat shock responsive genes are not time of day independent. And in fact, they tend to respond more during the early morning hours and less in the evening. And we think that part of this is because most classic heat shock experiments are done during the day, which is not actually when the plants are most tolerant. So in our data, we see that most plants tend to be more tolerant in the late afternoon, probably. This is just hypothesis because they've been accumulating those photosynthetes, but this is not when we do their experiments. And the point is that we know very little about what plants are doing at night. And yet for many stresses, this is actually when either the stress is happening or when they're most tolerant, or maybe even when they're most sensitive. And if we look at all of the gene expression data that's out there, so this is just from Arabidopsis, which has the largest number of expression experiments out there. Most of these experiments are done during the day. And a few of them are available for nighttime, but I have a star here because some of these are in constant light. So really looking at what a plant's doing in natural nighttime conditions is very, very limited. And I propose that this may be one reason there's such a disconnect between Arabidopsis experiments and field-based experiments, because of the concept of, we don't have normal night times in Arabidopsis experiments. But if we go beyond Arabidopsis and we look at field experiments, the bias is even worse. Very few field experiments are done at night. And so there's this missing aspect of the plant's life. And I would say for rice, I think most of these nighttime experiments are from my lab or my collaborators. So what we really need are field-based experiments monitoring this nighttime activity that combine both physiological and biochemical traits. And just as an example of this, in our study of warm nighttime temperatures, so we have been working in the field, because this is very hard to replicate the effects of warm nighttime temperature in a growth chamber. And so these are our field-based heaters here. The plants inside here are heated. These are our controls right next to it. Inside the heaters, we only turn the heaters on at night. So in the day, the control in blue here looks the same as the inside the heaters, which is in red. But at night, you can see the red coming up. And so we maintain, this is just across all of the nights, about a 2 to 2.5 degree increase in nighttime temperature. These plants are never getting a heat shock. They're still having this very large day to nighttime temperature difference. It's just that in the warm nighttime temperature within these heaters, that shrinks a little bit. They don't go down as far as at night. And we see a substantial, about a 10% decrease in yield with this subtle change. This is what other people have seen as well. But what we've done that is different is we went out there all night long and we sampled the samples both in the day and the night. And I'm just going to show you one example of those results from transcripts. We looked at metabolism and we looked at transcripts. And what we see is that really the time of day you take your sample. So these were the genes that were downregulated at dawn, downregulated when we did 3.5 hours after dawn. Really, we get a different cohort of genes depending on when we sample. So we see different. And so to get a full snapshot of what the effects are of warm nighttime temperature, it's really necessary to look at all of these. And for nighttime temperature, really we see most of the major changes happening with downregulation at night. And these are time points that most people don't sample because, to get out in the field at night is kind of a challenge. And this is not in concert with our diurnal activities. So we have a diurnal bias, and we believe that really influences our understanding of plant stress responses. And so for heat shock, which is kind of what we focused on, there's a fundamental difference between how plants respond in the day and how they respond in the late afternoon and how they respond at night. And we also observe this for other stresses. And we think this is particularly important for biotic stresses where there's a known temporal component because the pathogen's generally more active at one time of day or another time of day. And therefore, to fully understand really the effects of nighttime temperatures, but really any stress, we need field-based monitoring across that 24-hour period. And when we look only during our diurnal bias, we really miss half the life of the plants. And so our goal is really nighttime friendly field platforms for in-field monitoring. And it's not just as simple as walking out to the field and turning on your headlights and monitoring the plants or going out there with flashlight and collecting samples, because plants are very sensitive to those disruptions. And if you go out there, that will reset the clock of the plants. And we want to avoid that. So we really want to build an in-field platform designed around the challenges of monitoring at night, but that's respectful of the plant's internal clock. So we're not disrupting that. So we need to go out there with special equipment, headlights that allow us to monitor that. And we'd like to include optical measurements. So we've been pairing with Mike Kudinoff. And all optical measurements are really built around measuring stuff in the daylight when the solar spectrum is out there. A lot of the field-based work is developed around daylight assays. Even just monitoring growth or just the monitoring leaf movement, those are very challenging to do at night. So we're interested in night-adapted imaging for collecting and monitoring and connecting these to the biochemical aspects. So we have funding to work in rice, and that's like the model of high nighttime temperature stress, but we're really interested in exploring the effects of warmer nighttime temperatures in other crops. Sorghum, we have some lab data, and wheat, our collaborator has some data, but we don't have field-based data for any of these. So we'd like to move into those and look at that. And so we're looking for partners for that. And then just kind of as a plea, consider the nighttime effects. And as Chris was talking about earlier, with the generational and the transition to knowledge industry, our bias will influence the type of knowledge that we take. So we want to be sure to capture that nighttime knowledge as well. And I think if we think ancestrally, or even not even that long ago, a couple generations ago, the farmers knew what was going on in their field at night. Now, because of simplification, we've had to leave that out. And so I think recapturing some of that will be really important. And so I have a few people I need to acknowledge because the rice work was done in collaboration with IRRI, the International Rice Research Institute, and Krishna Jagadish, who's now at Kansas State, and Memetics, who I believe I saw some people in the audience for, helped us with the data analysis there. And really my collaborators on imaging are Michael Kudinoff, who is also interested in developing these tools for nighttime imaging, and metabolites with Sirius Lee at Plants for Human Health. Thank you.
Thank you, Colleen. Great presentation. And I was just told that congratulations are in order and you have been awarded tenure. So good on you. Congrats.
Thanks.
We have an offer for you from Craig. Craig would like to offer up his 2 crops for further study, potato and sweet potato. A major physiological defect in potato, internal heat necrosis, is thought to be brought on by high nighttime temperatures and drought. And sounds like a great project for a late night graduate student or 2.
For sure. Yeah, the people in my lab have to be night owls, or at least willing to be night owls for some.
No doubt. I remember some midnight plant collections when I was a grad student. I was glad to move off from that one, frankly. Colleen, I think.
Just bar hopping.
Say it again, Craig.
Oh, I thought that was you just bar hopping.
I should be so lucky. Any other questions for Colleen? I'm seeing some congratulations come in on the chat, Colleen. Seeing and hearing no new questions, we're going to move on to Ricardo Hernández. This is a bait and switch. The title that I gave is not the title that that Ricardo chose to use. So Ricardo, floor is yours.
Excellent. Thank you very much. Let me get this ready. And can you see the presentation skill or the slides?
We're seeing the presentation mode.
Excellent. Thank you very much for your
no,
time.
You may want to switch it. We're seeing presentation mode. We're seeing your notes and everything.
My notes. Oh no. Okay, no problem.
Yeah, pay no attention to the man behind the curtain.
We can fix that very quick. Not a problem. It should be good now.
There we go. Thank you.
Excellent. Well, hello, everyone. I want to start by thanking you for your time, since I understand you are under a very busy schedule. My goal for this meeting is to hopefully establish a line of communication and potential collaborations with the industry. Industry collaborators have helped fund significant number of research projects in my program. Consequently, the outcomes of the research have helped some of our partners. So this presentation will provide examples of research in my program in hopes that our expertise may be a match of your interest and lead to a collaboration. So I work in the area of controlled environment. I'm a trained plant physiologist, a degree in plant physiology and ag biosystem engineering. And I define controlled environment as the intersection between plant ecophysiology and environmental control technology. Controlled environments can range between grow chambers, tissue culture facilities, vertical farms, greenhouses, high-tech, low-tech, mid-tech. And my program serves all these sectors. Some of the examples of my current funded research projects are the indoor propagation of young plants, light optimization for lettuce production in controlled environment. This is an industry-funded project. Environmental optimization for nutraceutical indoor farming. This is also an industry-funded project. Molecular breeding for vertical farms using gene editing. This is also an industry-funded project. We're also working on strawberry propagation in controlled environments. This is mainly the initial efforts done with state funds. And we have a project in open field agrivoltaics with an innovative spectral beam splitting for solar collector. We're trying to split the visible light from the infrared light to use visible for plant growth and infrared for energy generation, electricity generation. This is federal funding. We have a project in environmental optimization for plant transformation. This is industry funding. And also light optimization for medicinal cannabis propagation and production. And this is also industry funding. So that's all the projects that we have currently funds for and working to deliver research results. But let me give you just a quick snapshot of some of the things that we have been able to accomplish in hopes to generate some interest. So we work with lighting. We work with lighting and using spectral optimization to grow specialty crops, a lot of them mainly horticultural crops. This is a video of my PhD student who is doing research with different light spectrums. Just to give you an example of the outcome, we work on dynamic light recipe, basically changing the color of light to try to improve plant growth or grow efficiency, or hopefully both. There's multiple ways you can approach this. This recipe came from background research that we did in the lab. And we were able to achieve, with the same amount of energy, just by changing the colors through the growth stage, 13% more dry mass on lettuce in growth, and also a 25% bigger head diameter. As a plant scientist, dry mass was of most interest because that's actually plant growth through photosynthesis. However, our industry partner was most interested in the head diameter of the lettuce. Being able to fill a clamshell faster was the main interest. So the impact of the research was shared with vertical farm growers and our stakeholders. Another example is the optimizing the propagation of strawberry in indoor systems. Growing a strawberry indoors, there is a lot of hype around growing fruits, strawberry fruits indoors. The strawberry tend to be a little bit less responsive to increases in light intensity and optimization of light intensity and CO2 when you're trying to produce a crop or a fruit. However, strawberry are way more responsive when you're trying to create vegetative matter. And every single strawberry plant produced in the United States comes from a clone, one of these little plants coming from the mother plant. And currently, that the way propagation is done has a lot of intrinsic problems and pathogens. So one idea was to do a proof of concept and see, we move these plants and we create an environment, they neutral strawberries, to make them produce more plants per mother plant. So we did a proof of concept, and don't bother looking at the figure, but we were able to match, we were able to achieve 5 to 10 times more young clones and daughter plants per every mother plant in the same amount of time than the current conditions. I was expecting 25, maybe 50% increase, but we are at to 10-fold increase. So now we're working in seeing on how see if we can try to revolutionize the way strawberry propagation is done in the US. And another project is cannabis or cannabinoid optimization and environmental characterization. Since hemp became legal in the state, we decided to do research on hemp to try to characterize the responses, its responses to environment. While doing that research, and continue to optimize plant growth, we are both optimizing the propagation of these young plants that will eventually go to the field, and also the production of not only the mother plants, but also of the plants used for medicinal purposes and extraction. Here you have a greenhouse. We have a greenhouse full with these plants, quite aromatic. But the plants are being grown right now, and we hope to get results from this research soon. Some of the impact of this research is that the results have been shared with producers, and also the initial efforts help secure funding for our entire new research program coming from the industry. So all this work I take credit for all the work, but the actual work is done by my grad student, postdocs, and research technician. So they deserve all the credit. And this is my presentation, and I will stop here to address any questions. Thank you.
Thank you, Ricardo. Always enjoy listening to what's going on in your lab. Questions for Ricardo? Okay, hearing none. Ricardo, I think you're going to be available at one of our networking tables at 5, right?
Absolutely, absolutely. Thank you very much.
Thank you. And Anna Stepanova is up next.
Yes, I would need your permission to share my screen. I don't have a permission.
I think, okay. Somebody help.
If you're the host, you should be able to make.
Yes, I should. And if only I could figure it out. Hang on a sec.
Okay, I have the permission now. Thank you.
Oh, great. That must be, Jeff must have done it. Thank you.
All right. Now, can you see my slides?
Yes, we can.
All right. Hello, everyone. I want to thank you for this opportunity to share with you some of the work that we do in the Alonso Stepanova lab here at North Carolina State University. I am a molecular geneticist by training and have been studying the mechanistic basis of plant hormone function for over 2 decades. But in the past few years, my research interests more and more shifted towards using synthetic biology as a tool to address long-standing questions in plant biology and hopefully provide elegant solutions to the technical bottlenecks that we encounter in our research. Today, I will talk about one ongoing, unpublished synthetic biology project in the lab that is poised to overcome some of the technological barriers that we face when we need to express genes of our interest in specific spatiotemporal patterns. Biology research is often restricted by the choice of promoters we have available to us to drive the expression of genes of our interest in complex patterns or at desired levels. We often rely on the so-called markers, such as tissue-specific or stimulus-inducible promoters, that enable us to target our genes of interest to specific cell types or to trigger expression of our favorite genes at will. But how specific or noise-free are those markers? And the answer is not as specific as we would like them to be. For example, some of the best root-enriched markers have detectable shoot activity under some conditions, or the best epidermis-specific markers often show low levels of some epidermal expression. And this leakiness of the best tissue and stimulus-specific marker genes is a widespread phenomenon in plant biology. Nonetheless, in molecular genetics, we often express genes of our interest under the control of the promoters of those enriched, but not necessarily very specific genes. And we make conclusions based on our ability to complement. Furthermore, for some tissues and stimuli of interest, we do not have good promoters. And we started wondering if there's a way we can derive new patterns of expression, starting with a limited collection of existing natural or synthetic promoters. In theory, new, more specific patterns of gene expression can be obtained using genetic devices that recapitulate Boolean logic widely used by engineers. In simple terms, one can restrict expression of a gene of interest if conditions A and B are met using the so-called logic AND gate. In our case, the gene of interest will only be expressed in tissues where both A and B inputs are simultaneously active. For example, if A is a root quiescent center enriched marker that has leaky expression in the shoot, and if B, let's say, is a root specific driver with a broader domain of expression, we should be able, by combining those two inputs, to restrict the output gene just to the tissues where both coexist, which is the root quiescent center. And this is, again, is called a Boolean AND logic. Likewise, many other derived patterns of expression should be obtainable from the same initial two inputs using other types of basic logic gates. But how can we accomplish that at the molecular level? Several methods have been devised. For a molecular person that works with genes and proteins, the easiest thing to visualize is how a heterodimeric transcription factor can be used as a logic gate. For example, in a heterodimeric factor that requires both A and B subunits to be active, you will only be able to activate the output gene if the two monomers are co-expressed in the same cells, whereas either A or B alone will fail at activating the output gene. These types of transcription factor-based approaches are powerful, but have very limited scalability due to a finite number of characterized transcription factors and suffer from cross-reactivity and leakiness issues and can only be recreated for some logic gates. So we propose a new system that overcomes these critical limitations. Our system is based on CRISPR and tracer RNA as the A and B inputs that hybridize to one another to form a dual guide RNA. They assemble with a nuclease-dead version of Cas9 that is converted to a transcription factor through being fused with the transcriptional activation domain. If CRISPR is driven by our quiescent center enriched WOX5-like promoter that is also having leaky shoot expression, and then our tracer RNA is expressed under a broad root enriched promoter, and then our Cas9 transcription factor is ubiquitously produced because it's driven by, let's say, ubiquitin 10 promoter, the output gene will only be active specifically in the quiescent center. That's where all three inputs overlap. So the key advantage of the system is that it is highly scalable, it's tunable, and it's compatible with all basic logic gate designs and is easy to what we call wire. Let me explain what I mean by those things. So where does the scalability come from? For the functional guide RNA Cas9 ribonucleoprotein complex to form, the CRISPR RNA shown here in green and the tracer RNA shown here in black need to base pair to one another. And disruption of base pairing through mutations in this lower stem region of the paired region of guide RNA abolishes Cas9 activity. So here is shown as non-complementary pairs. Whereas if we restore complementarity by introducing mutations in the partner RNA, we're able to restore Cas9 activity. So we reasoned that we can take advantage of this base pairing requirement and generate multiple pseudo-orthogonal, that is non-cross-reacting, CRISPR RNA, tracer RNA pairs that can work in parallel in the same cell with a single Cas9 on different DNA targets. That would, in theory, permit the coexistence of independent logic gates or of a single multi-gate genetic circuit in the same cell. Here is a hypothetical example of three co-expressed pseudo-orthogonal AND gates that collect the input of 6 different promoters of interest, driving 3 pairs of guide RNAs to independently control 3 different genes through a single Cas9. Here's an example of a single triple AND gate circuit where 4 promoters drive expression of 2 pairs of guide RNAs to control expression of a 3rd guide RNA pair that regulates the expression of a single final output gene of interest, all through the use of a single dCas9 transcriptional effector protein. By regulating the copy number of target protospacer regions within the promoters of genes of interest, we in theory should be able to tune the levels of expression of the output gene by controlling the number of guide RNA Cas9 complexes that are recruited to the promoter. This is not a strictly linear relationship, but in general, the more protospacers there are, the longer is the activation of the output gene. And to further illustrate the hypothetical potential of our approach, I'm showing you the predicted patterns of expression in the root tip one would get by combining a tissue-specific native promoter such as WOX5 with a synthetic ethylene-inducible promoter, 10xEBS, using all 8 basic logic gates: AND, NAND, OR, NOR, XOR, XNOR, A not B, and B not A. So So none of these derived patterns of expression are available in nature. So we believe the potential of our CRISPR-based logic gate system is quite huge. The CRISPR-based logic work is funded by the National Science Foundation, and this is an ongoing career project that started in October of 2018. And given our group's expertise in plant hormones and in synthetic biology, as a proof of concept, we are generating and testing these genetic devices in transient assays in tobacco, and then we'll eventually employ those devices to precisely control the expression of our favorite auxin biosynthesis genes in Arabidopsis and tomato to manipulate plant root architecture. To show that our dual guide RNA approach works, we built several basic 3-input logic AND gates that converge on the activation of an M-cherry reporter. Different versions of guide RNAs that we've tested correspond to the unprocessed and processed versions of CRISPR and tracer RNA. And from our experiments, we see that in transient assays, only the short versions of guide RNAs give us a strong output reporter signal, as shown here. So that suggests that RNase-mediated processing of full-length CRISPR RNA may be rate-limiting in plant tissues. So for all of the follow-up experiments that I will show you, we are using short processed versions. So we next generated 4 mutant but complementary pairs of the CRISPR and tracer RNA that harbor 1 to 5 mutations in the lower stem region of the CRISPR tracer pair and compared their ability to form functional complexes with dCas9 and turn on the output M-cherry reporter gene, as shown here. As you can see, all 4 were functional and comparable in their activity to version 1, which is our wild type reference. Even the guide RNA pairs with 5 mismatches, but complemented, so 5 mutations, but still complementary to one another, were functional. With 5 versions of CRISPR and tracer RNA at hand, we could then run 25 5x5 pairwise combinations to test the orthogonality of mutant pairs and determine how many mismatches in the lower stem regions are required to disrupt the base pairing. And these combinations contain 1, 2, 3, 4, or 5 mismatches, as indicated by the red crosses in the individual boxes. And what we see is that full output reporter activity is only seen in perfect match combinations. And a single mismatch in the lower stem region is enough to dramatically reduce the reporter activity, whereas 3 or more mismatches in the CRISPR and tracer RNA lower stem are enough to completely disrupt the dCas9 mediated activation of the reporter, as shown by these white boxes. So we went ahead, and so I'm going to show you some of the specific data for this representative table. Here is a wild type pair, wild type with wild type, and this is mutant with mutant, so still complementary, so we get plenty of M-cherry activity. And then we're checking the mismatched combinations, in this case with 5 base pairs that are different between the CRISPR and tracer RNA in the stem. And you can see that this 5 base pair mismatched versions give us no activation of the reporter. This is an example where we are doing sequential 1, 2, 3, 4, and 5 mismatches, and we can see no activation of M-cherry, our output gene, when CRISPR and tracer RNA harbor 3 or more mismatches in the lower stem region, whereas there's still some activation with 1 or 2 mismatches. What this means is that with just 5 base pairs of the lower stem to mutate, we can generate multiple sets of up to 16 orthogonal CRISPR tracer RNA pairs that are different by at least 3 bases, allowing us an unprecedented level of logic gate multiplexing. And if we introduce the upper stem of CRISPR and tracer RNA into equation, even a greater number of orthogonal gates can be multiplexed. In fact, our preliminary data suggest that upper stem mutations do affect the ability of CRISPR and tracer RNA to pair. Here's an example of a guide RNA pair with 12 upper stem mutations. What we did is we swapped the 12 terminal nucleotides between CRISPR and tracer RNA, preserving the sequence complementarity of the pair. And as you can see, this mutant U12 pair still works, resulting in the activation of the M-cherry reporter. In contrast, the reciprocal combinations with mismatched upper stems either greatly reduce or fully abolish M-cherry activity, suggesting that we can further expand our toolbox and extend the number of orthogonal CRISPR tracer RNA pairs that we can build by leveraging upper stem mutations, possibly in combination with lower stem mismatches. We also constructed 2 pseudo-orthogonal pairs of trace RNA that work with their respective target protospacers to activate 2 different fluorescent protein genes. In one case, it's anteri, in another case, it's YPET. Like matching combinations, non-complementary pairs with 5 mismatches in the lower stem regions fail to activate the output genes, confirming the lack of cross-reactivity between the logic gate pairs. And here are the actual data. Matched combinations give off fluorescence of the expected wavelength, whereas mismatched combinations do not, confirming the full orthogonality of the 2 guide RNA pairs. To summarize what I told you this evening, we succeeded at implementing Streptococcus pyogenes dual guide RNA CRISPR-Cas9 transcriptional activation system in tobacco transient assays. We see that orthogonal guide RNA pairs can work, and we can make them by just simply introducing mutations in the complementary stem regions of CRISPR and tracer RNA. We now know that 3 or more mismatches in the CRISPR and tracer RNA lower stem fully abolish output reporter activity. Upper stem mutations in the CRISPR tracer pair greatly reduce or block the output reporter function. And finally, while all this was just a proof of concept work, we will employ this system down the road to generate orthogonal CRISPR-based genetic logic gates to precisely control where local auxin biosynthesis takes place in roots to manipulate plant root architecture. And with this, I want to acknowledge my collaborators and my lab personnel, and take any questions if you have any.
Thank you, Anna. That was great. Questions for Anna? And Anna, you're going to stick around for the networking, I think, right?
Yes, I will.
Wonderful. So if there are questions, then we can ask them. I want to thank all of you for joining us.